For topic 5, we're going to look at solving trigonometric equations in a quadratic or a factored form. So for equations in a quadratic form, remember, we're looking for something that kind of fits this format. Well, let me fix that. Gracious. Equals 0 or equals some constant or something like that. So we're looking for something where you have a value and then you have that same value squared, okay? So kind of like where we have the x and then we have the x squared. So what we do is we let u equal the variable expression whose square is also in the problem. We substitute in u and then solve the resulting equation, which is going to be a quadratic, and then you do back substitution to basically get your actual solutions, okay? Now, if you're dealing with something in factored form, we had this thing like back when we were in 171, where if we had, let's say, A, and then we had B, and it was equal to 0, we could use this thing called the zero product property because we knew if we have a product equaling 0, at least one of these things or both of these things have to equal 0. So when you have something that you can factor and write it in a factored form or something that is automatically in a factored form, if you can get it factored and equal to 0, then we can use that zero product property to help us solve. Okay, so let's look at one of each. Okay. So example 7 says solve each equation when theta is from 0 to 2 pi. So again, solving from 0 to 2 pi is pretty standard, okay? So first we have 2 times cosine squared of theta minus cosine of theta minus 1 equals 0. So we could kind of think of this, it looks almost like 2x squared minus x minus 1 equals 0. So it looks very quadratic in nature. So what you do is you always look for the basic expression and let it equal u, okay? So this is our basic expression. We have that expression squared in our equation. So you always let the basic one, like to the first power kind of, equal your u. So what we're going to do here is we're going to say, okay, we're going to let cosine of theta equal u, okay? So off to the side, state what you're going to let u equal. So u equals cosine of theta, and don't forget that because we're going to have to come back to that idea of u because essentially we're going to rewrite this equation, replacing cosine and cosine squared with u and u squared, and then we just have like a regular old quadratic to solve, and then we have to come back to this idea of, hey, u was really equal to cosine, okay? So if I let u equal cosine, this gives me 2u squared minus u minus 1 equals 0. So we would want to solve this quadratic equation, and there are a couple of ways that you can solve, well, there's several ways you can solve quadratic equations, but the two most popular were to solve by factoring if you could, and then to use the quadratic formula. This one's factorable, so I'm going to factor this one. So because I have a coefficient on the squared term, I'm going to use what we call the AC method, where I take the coefficient of u squared, so 2. I take the constant, -1. I multiply them, so I get -2. And I want to find two numbers that multiply to give me -2, but then add to be the coefficient of just u. So they need to multiply to be -2 and have a sum of -1. So I could use -2 and 1. So essentially what we do is we rewrite this middle term as two terms where the two terms have a u and then a coefficient of -2 and then +1. So I'm going to rewrite this as 2u squared minus 2u plus 1u minus 1 equals 0. So I've essentially split the term -u into the sum or difference of two terms, being -2u plus 1u. So if I were to combine like terms, I would just get -u. And now I can do something called factor by grouping. So that's where you kind of split these in the middle, and then you factor each half. So if I look at 2u squared minus 2u, I can factor out 2u. And when I factor out the 2u, I basically divide both of those terms by 2u, which leaves me with u minus 1. And then on the second half, the right-hand side of this equation, I have u minus 1, but I still have to factor something out. So I can factor out just a +1. And when I factor out +1, it doesn't really change anything. So then I need to break this down. I need to officially factor this. So I now have a GCF, we'll say, of u minus 1, and it leaves behind a 2u plus 1, and that all equals 0. And then we have this factored form, so we can basically take each of these factored pieces, each of these factors, and set them equal to 0 and solve. So I get u minus 1 equals 0, and 2u plus 1 equals 0. Well, if u minus 1 equals 0, then u equals 1. And if 2u plus 1 equals 0, then 2u equals -1, which means u equals -1/2. And we're not done, okay? So like if we were in just a regular algebra class and we were solving this equation 2u squared minus u minus 1 equals 0, we would be done. But we're not done because this all started from a u substitution. So remember, we said that u was equal to cosine of theta. So each value of u we need to set equal to cosine of theta. So I'm going to say, okay, u, which is really cosine of theta, equals 1, and u, which is really cosine of theta, equals -1/2. Okay? So we need to think of what values for theta give us a cosine ratio of exactly 1. Well, cosine equals exactly 1 when theta equals 0 radians. Okay? And then we have to ask ourselves, well, where is cosine equal to -1/2? So what values of theta give us a cosine ratio of -1/2? And that happens at theta equals 2 pi over 4 and 4, or not 2 pi over 4, 2 pi over 3. Hold on, I don't know why I put a 4 there. So a 3 and then 4 pi over 3. And if you need to look at your unit circle, use your unit circle. Work really hard at understanding how to build it, and then from there kind of work on trying to remember some of those really important values. So let's go to the unit circle. We're looking for angles where we get a ratio of 1 and a ratio of -1/2. So I may have writing on here from previous examples. I do. So let me erase that, that, and this. Okay, so we want to know when we have a cosine of exactly 1. So remember, our ordered pairs are always x is cosine, y is sine. So cosine is going to equal 1 right here at 0 degrees or 0 radians, and it never equals 1 again. And so when we have these quadrant angles, most of our ratios repeat. So like all of the ratios that are not on the quadrants, not quadrant angles, they repeat. You'll get them all twice, but the quadrant angles don't necessarily repeat. So cosine is exactly 1 at 0 radians, and then we want to know when cosine is equal to -1/2. Well, cosine is -1/2 at 2 pi over 3 and 4 pi over 3. And those are the solutions that we got over here. So we got that theta was equal to 0, 2 pi over 3, and 4 pi over 3 radians. Okay? Now for part B, we have tan of theta, or tangent of theta minus 1 equals secant of theta minus 1, and that product equals 0. So we have essentially a factored form equaling 0. So we can go ahead and apply the 0 product property. We can say, okay, well, our first factor, tan of theta minus 1, can equal 0, and our second factor, secant of theta minus 1, can equal 0. Okay? So we need to solve each of these individually. So I would say, okay, well, if tangent of theta minus 1 equals 0, then tangent of theta equals 1, and secant of theta, if secant of theta minus 1 equals 0, then secant of theta equals 1. Okay, well, tangent we're pretty comfortable with. We can continue to use that. But if you wanted to, you could use a reciprocal function for secant. Okay, so we could do this kind of two ways. Well, do I want to solve that one this way? Yeah, I think I like using cosec or cosine instead of secant. I was going to say, is it going to be any easier? It really will. So remember, we can have the reciprocal functions. Okay, so secant is the reciprocal of cosine, and cosine is something that's exactly on the unit circle. So there is going to be a perk here to going ahead and converting the secant function to the cosine function. So I'm going to write this as cosine of theta, but remember, they're reciprocals. So for whatever angle we get, sine and or cosine and secant are going to have reciprocal values. So think of this as 1 over 1. Well, the reciprocal of that is 1 over 1, or just 1. So essentially we need to solve for cosine of theta equals 1. So we're looking for when does tangent equal +1 and when does cosine equal +1. Well, cosine equals +1 when theta equals 0 radians. Okay? And then tangent equals +1. Now we have to be a little bit more careful with tangent. Whoops. Is it going to let me erase? There we go. Okay. So remember, tangent of theta is equal to sine of theta divided by cosine of theta. So we need to find angles where the ratio of sine and cosine are going to be +1. So this is going to occur at two different places. And this is going to be when we have that sine and cosine are the same, like exactly the same sign, same everything. So this is definitely going to happen at pi over 4 And then it's going to happen again at 5 pi over 4. So let's go to our unit circle and double check. Okay? So if we go to the unit circle, remember we got some old stuff in there. So let me do a little erasing really quick. Okay, so we're looking for when cosine equals 1. So cosine is 1 at 0 radians. We already know that. But then we're looking for when tangent is equal to 1. And that's going to be when cosine and sine are exactly the same. So cosine and sine are exactly the same at pi over 4 radians, and then they're exactly the same at 5 pi over 4 radians. And that's exactly what we have on our worksheet. So if I were going to write this out formally, I would say, okay, theta is going to equal 0, pi over 4, and 5 pi over 4. So that's how you can take these equations that are in like a certain format and still solve them, okay, using either U substitution or just understanding how a product equals 0. Okay, so you can use that zero product property. All right.